Mark, can you just close the door, please? Okay, so we're going to look at a new topic, and it's abbreviated as PDC. I hadn't even heard of PDC till about in December when I attended a conference, and it stands for Parallel and Distributed Computing. So if I'm teaching you guys a course on distributed systems, I figured I better teach you this big area. So I figured at some point I'll be able to add some more slides, and today is the point. So high performance. Nircha attended the Monday talk, the faculty recruiting talk. I think you were there. And we saw that with data science, how important high performance is. And this is when computers are relatively fast today. Just imagine the days when the computers were not that fast. And the hope was that you would just collect together computers to solve problems, even the traditional ones, not the new data science problems. Okay? So that's the motivation for high performance. And this has been there's been a whole evolution in this area. And I'm going to show you some of the latest and greatest soft abstractions. And I've got their names here. So OpenMP is for parallel computing. The assumption is that the processors are connected through a hardware memory. But if we go and add a software abstraction, so you can actually add a software abstraction that uses all the IPC stuff you guys have learned to give you the illusion of having a distributed shared memory. So if you have that, then this OpenMP, these concepts also apply to distributed computing. Okay? And MapReduce is something that's been created just for distributed computing. And so is OpenMPI. OpenMPI is pretty much like sockets. It's just a different syntax. The abstraction level is the same. So we won't look at that. Okay, sockets or NIO that you guys looked at. And OpenMP is, why do I think it's latest and greatest? Because there are courses in our department that use them. So Jan Prince's 633, which you guys were asking me about last when registration opened, uses OpenMP, and Don Smith's 590 course uses MapReduce. Okay, so these are the courses that will look at the stuff in real detail. And my goal here is to relate them to each other and to what you've done earlier. Okay, so that's the main thing. That's the main goal here. That what you've been doing has also been parallel in distributed computing. We've been doing distributed computing, but we've seen that we need threads to do distributed computing. So you know the mechanisms, and so we'll try to go and figure out what the relationship between them and abstractions just meant for high HPC are. Okay, and I'm also going to try to connect them to the research with which I'm familiar. I don't do research in this area, but I do listen to a lot of research talks. So we'll connect them together also. Okay, and OpenMP and MapReduce and OpenMPI. If you go and do a Google, you'll find lots of documentation on this stuff. So there's not much mystery here as to what they do. But what I'll try to do is derive them from first principles and explore why they are the way they are rather than what they are. Okay? Questions so far? So, way back when we started the course, I gave you a lot of examples of distributed applications. Okay? A remote printer or desktop, a replicated file or database, some data store, collaborative applications, and your assignment involves a collaborative application, in fact. Distributed sensing, that you've got data at different locations that have to be aggregated and made sense of, and something that does some distributed algorithm like matrix multiplication. So I'm going to divide these guys into two camps. And can you see why I made this division? Or can you see some criteria? Can you identify some criteria that justifies this division? There can be multiple criteria. Yeah.
The green one, algorithm one, doesn't need sharing like system stuff like memory. The
So you're saying the green one doesn't require sharing of any system resources, whereas the pink ones require sharing of some system resources, perhaps. Okay? Because there's no, I mean, this is just a matrix we're multiplying. There's no resource that we're talking about, so that's good. Anything else? Yeah.
I think like the green one's more like just number crunching. So it's just like parallel. You just need to somehow compute this whole massive data. But the other ones actually have to sneak resources.
So he said what the green ones, what the pink ones do, they share resources, and you're telling me what the green ones do. They're number crunching, and it's meant to actually. So why did we go distributed? We needn't have done distributed parallel matrix multiplication, right? You've all seen my matrix multiplication that is single-threaded, and we went to parallel distributed because we wanted to speed up.
But then you're still sharing stuff, right? In the distributed matrix multiplication, you still have to use IPC to finally add up all the individual.
So there will be some sharing and thing, but he said resources. Okay, by resources he was talking of OS-like resources or persistent resources. So in one case, so the line is blurred. That's good. Okay, and that's why the similar mechanisms will be used in both kinds of problems. But in one case, the goal was to take something and do number crunching or to speed up an algorithm. In the other case, there were other goals. And maybe an easy way a simple way to say that is that we wanted some kind of sharing of system resources. Okay? So distribution reason, and we'll qualify that. Okay? So in the top one, we are doing a remote service. Okay, which lasts for a while. Okay, here we are. Why are we creating replicated repositories? Why not just create non-replicated repository?
Because you want multiple people to be able to work, and if you're creating a non-replicated repository, just becomes a complicated error. Like version controlling becomes harder. You're basically also if you're doing a single repository and there's two people working on it at the same time, you're literally doing a commit after every single thing you type, because the other person needs to see that update. Right?
So what you're saying is that the choice is between replicated and version control. So do you create the exact replica on all sides, or do you allow divergence or not?
No, I'm saying that we can allow divergence. It's just that if you want to allow divergence without replicating, it just becomes extremely slow.
How can you have divergence if you haven't replicated? If I just have a central resource, then I just have one copy.
I mean, yeah, I guess, sure. Okay.
So replicated might be to allow versions, okay? And that's something that, software engineering talks a lot about. In distributed computing, we often do replicated because we haven't talked about this much in detail because we haven't looked at Paxos, which solves a certain problem. But why might you replicate some data? Yeah.
This is kind of intuitive, but redundancy in case you lose something and you can go to backup.
I always tell you guys that make sure your code is backed up in Dropbox or Google Drive. I have had so many classes where students have lost their code. Fortunately, we have the old versions in Sakai, and so we are able to give them. So fault tolerance is a big deal. Okay, and we'll look at fault tolerance more when we look at Paxos. But we haven't looked at that at all. But fault tolerance and also availability, as we'll see. Okay, but fault tolerance is a big reason. In collaboration, why did we have a distributed program?
Yeah.
Exactly. Okay, it's obvious. Okay, you've got distributed users. You're not doing the same computer. You might be doing the same computer, actually. You guys are in this, you guys all have your workstations. So when I was a grad student, we all had one time-sharing system, and we would have different terminals to it, and we would play games, collaborative games, all using one computer. Okay, so it is possible to have collaboration with a single computer, but you're right. In fact, you can also have collaboration with the same keyboard and mice and screen. So at Xerox, there was a system called MMM, which is multi-mice, and the idea was you could actually do tug of war with two different users, with two different mice on the same screen. So You can have non-distributed collaboration also, but in general, you have distributed collaboration. And similarly, the distributed sensing, the data are distributed. Okay, so you need to go and collect from distributed resources, so you can't but have a distributed program. Okay, so these are all the reasons, and you can say it's resource sharing as sort of a general classification. But here the idea was speed up. We can do it without distributed computing, but or parallel computing, but we'd like to use them just so that we have faster number crunching. Okay, but that's the primary reason. Once we build this distributed program, it's not that performance is not an issue, right? So a secondary reason, once you build this, you might want to later speed up your algorithms, each of these servers. And like you said, you're going to have some kind of copies of data and you have to aggregate them together. So the secondary reasons become primary reasons in one case, and we have them as second reasons in the other case. Okay? So that again shows you that there's not a very clean line between them. Okay? Questions? Okay. In both cases, you can say that, look, we've got some existing program that's non-distributed, and we are migrating to and making it distributed. Okay, so in the file server case, we might have had a local files process system, and we are making it remote. Okay, I could have had a solitary game, and I'm making it a distributed game. In your assignment, you saw that we took a single user program simulation, and we have a multi-user thing. Okay, so let's go and see how sort of the evolution occurs in the two cases. Okay, so here we saw that in your assignment, you saw that in that you go from a non-distributed program to a distributed program, and when you create a distributed program, you also end up creating threads. Okay. If you've got a non-distributed existing thread program, you might want to first go to a non-distributed multi-thread program. Okay. And then if you don't have enough threads on one computer, and if you think your competition can handle the communication costs, you might go to then a distributed program. Okay. And each of these distributed programs may in themselves have threads. Okay. So if you could thread it once, you could thread it also multiple times. Okay. And you might go from a non-distributed program directly to a distributed program without even going through the intermediate step. Okay. So the history may be different, but what you've ended up, again, the structure looks very similar. Okay, you have processes with threads in them. Right? And the threads we create in the speed up case for concurrency. Okay, you're hoping that these threads go to different processes. Now, why exactly did we need threads in the non-speed up case? What are some of the reasons we needed threads? Why couldn't we have just had our distributed programs have a single thread in them?
For which case?
Yeah, so, yeah.
Interactivity in the program.
Interactivity, okay. We didn't want to select thread to block, right, Tegan?
I was going to say that basically also, communication while you're also doing something on the application, and you don't have to do one or the other.
Yeah, you don't have to do one or the other. Okay, you don't have to serialize things, you could do concurrently. What about your exam question? If you didn't have threads, could you have done it? Given RMI, you couldn't have actually had that output if you didn't have threads. Right? And you're going to also see in your assignment 4 that if you didn't have threads, you would have deadlocks. Okay? So this is a lot of text here, mainly for you guys when you study that you can look at the PDFs, but basically repeating what I just said. That we saw that when you have sockets, you need a thread per socket that you're reading. Okay, otherwise you don't know into which order to block. Because we've got a synchronous primitive, you need threads. We had the non-blocking IO, that should have been NIO rather than NIP. The NIO selected thread sends data to the read thread, again for reducing latency. And creating a separate thread for incoming remote calls. We saw that in the exam. And in assignment 4, make sure you do that, because otherwise when you have synchronous remote procedure calls, you'll end up with the deadlocks. Okay?
So how do two threads avoid a deadlock? Don't two threads cause a deadlock? Like if you have two locks and you're acquiring them in their wrong order, and then both threads take one lock, and then you have a deadlock. But how does a third thread help you avoid a deadlock?
That's interesting. So deadlock involves multiple parties. And what Nijjhar is saying is that when you create more threads, you create more parties. So there's potential for deadlocks. So how come threads can solve deadlocks? Think distributed programs.
Can't you have one thread that's managing to make sure that you can have basically a watchman thread?
Okay, that's interesting. There's a lot of work on deadlock avoidance and prevention.
That's something I remember
So-
from 530.
So you could have a thread like that. That's good. Yeah.
You could also have a thread that can eventually unblock one of them. If it takes too long, you can usually call.
So you could-
or notify.
So that's kind of the same spirit that you have a mediator that does that. Think of callbacks. Client makes an invocation on a server. Server calls back in the client. What if it's all being done in a select thread, for instance? Your select thread in the client is blocked, waiting for server's result, and it's not even willing to go and invoke its callback because it's waiting for the server thread to finish its call. And if it's all blocking, if RMI did not create a separate thread, then you would, for each incoming call, then you would run into this problem. So basically, when the calls occur through another process and come back, it's better if when the call comes back, it executes in a separate thread than in the thread that made the call. Okay? And you'll see that again in assignment 4. That you will actually, if you don't do this, you will end up with a deadlock. You get that?
So it's better for a callback to go through a different thread than the thread that's sent.
Yeah, you have thread T in the client that invokes a method in the server. And the server makes a method back in the client. And to service that call, you need thread T's intervention.
But is blocking the same as deadlock though?
It is deadlock, right? Client is waiting with the server, server is waiting with the client.
Yeah, sure. In that sense, yeah, sure.
In Europe, they call it deadly embrace. A little bit more colorful there. That neither one is willing to give up the embrace. Did you get that then?
So when the server calls back, because it's not a separate thread for it.
Yes.
it's on the-
Yeah. So when the server calls back, that message is being processed has to be processed by,
Because the first thread is already with its call is in the middle of calling. its
and look at your NIO implementation. If it was a select thread, if the select thread made the call,
it would, yeah.
it would involve the select thread, the server, and then it will send back a message which has to be processed by the select thread.
Right.
So in assignment 4, what you have to do is create a factory, register a factory that goes and says, do not invoke method calls in the select thread, invoke them in a separate thread, and they're related by the producer-consumer relationship. And I don't do it by default, firstly to sort of show you this problem, and secondly to avoid the context switching problem. Okay? So that's the reason for creating threads. Okay? And in the speed up case, you can first do thread decomposition. I'm just showing you the relation between process and thread decomposition. So in the pink case, we have the process decomposition first, and then we create threads afterwards. Here you might have the first single thread, then you replace it with multiple threads. Then some of these threads can be replaced with processes. Okay, and your extra. So for instance, if you're doing matrix multiplication, you can have each row handled by a separate process, and then threads within that go and multiply the row with different columns of the other. Okay. So again, you end up with the same structure, but the history is a little different. So the way you program, the way you think about the program is a little different. Okay. Questions? Okay, so you guys have been doing distributed programming. You haven't seen Paxos, but what's been the algorithmic challenge in your assignments? There's implementation issues, and there's algorithmic issues. Algorithmic is, the general algorithm. Okay, whereas the mechanisms could be an IO or it could be RMI. So from an algorithmic part, what was the interesting or challenging part in your assignments?
Figuring out two-phase commit.
Two-phase commit. Okay. And so there was non-atomic broadcast, which was the simplest. Then we did atomic broadcast. Okay, that was a different algorithm, just kind of simple. And then two-phase commit. Okay. And like I said, Paxos, in Paxos, we won't even have a central process. Okay. So,
Commit in non-atomic also very interesting, but we have to go back and reverse whatever happened already in the first plan.
sorry, say that again.
When you have two-phase commit and the mode is non-atomic, one plan has already done the proposed change before it actually got.
No, I don't think so. Did you implement that?
Yeah.
That was not meant to be implemented.
Okay.
No undo was required there. But yeah, if you want to do undo of any kind, that's the thing. So it was specific atomic. They were both atomic. In one case, it was one-phase atomic without the guarantee of consistency, as much guarantee of consistency as. Atomic just meant that they executed the procedures in messages in the same order. In two-phase, we also make sure that everybody says okay before you execute an operation. Yeah.
Can you run two-phase commit in non-atomic mode?
Now, he's tried to do some. He's tried to.
Yeah, that's what I'm saying.
He's tried to invent a variation of it.
Well, we weren't supposed to do that, right?
No, you're not
We're only
supposed to.
supposed to do two-phase commit in
Yes.
atomic.
Yeah. Okay. So the challenge is basically consistency. That you've got these processes, they have to be coupled in some way. And we want to make sure that the coupling is what we want. Okay. And here, the challenge is how do you take something that was created single-threaded and made parallel? And how tough do you think this challenge is? Easy. Now that you guys know, you know threads. Are you licensed to do anything?
It depends a lot on what you're doing. If the problem you're already solving is iterative, then you can distribute iterations across machines. But if the problem you're doing is non-iterative, then it can be very difficult to truncate across machines.
So there are two challenges here. Yeah, I mean, it depends. Iterative also, trust me, it's still not, parallelizing for loops is not that easy. Okay, and so there are two issues. Firstly, there's the algorithmic part and they go hand in hand. But one of our students who did well in industry, I was asking him, what kind of bugs do people make? And he said, basically two classes of bugs, he says again and again. One is handling user input. When the unexpected user input occurs, the program goes and that's why we get blue screens, right? And the other was concurrency bugs. Okay? And those are bugs. The whole idea of parallelizing is to get speed-ups, and you might mess up and not get the desired speed up. Okay? And that's why you need to take 6633 to learn about that. Actually, Jan was supposed to come today, but at the last moment he couldn't, so he'll hopefully be here on Tuesday. And you guys can talk to him after class about what he'll do in 633. And hopefully by that time he'll have more motivation. Okay? And to reduce the algorithmic cost, we use two-phase commit rather than when we'll see Paxos. So the idea was that we often have the clients talk to each other. The clients that need to be coupled with each other talk often through a server to make the algorithm easy. Okay? So there's a central process through which other processes talk. Does that make sense with speed up also? The notion of a central mediator? Because
what they said earlier, you have to eventually get one. You have to combine them.
you have to combine the results and maybe you have to split the results too. Sometimes the data themselves might be distributed, okay, in a distributed case, and that's what map reduces about. But you might want to combine results, okay. So again, you have central process and other processes, and in one case we'll call it server client, in the other case we'll call it master slave. Why am I not calling it server and client? So do you guys remember the definition of server and client? Yeah.
We had some sort of intuition that server is usually smart and the client is usually a dumb.
That was your intuition. Okay, which I contradicted and I didn't like that. Okay, yeah.
Aren't servers unaware and the clients are aware?
Yes, that was the way you have to, so client is aware of server, and the server is not aware of where the client is, and the clients can come from all over. What about in the distributed computation case? If there's a master that's creating getting the data, it's probably creating the slaves. So it can be quite aware of them. Okay, so I wouldn't call it a server. Now you might have cases where you're trying to solve the meaning of life, and you've got a server that's trying to do it, and everybody offers their own client and joins the server and says, "Okay, I'm joining you in your quest." But mostly it's a short-lived computation, and we don't have that case. Okay. Question? Okay. Implementation challenge. I'm going to look at Gatti. So what was hard about assignment 1?
Figuring out what goes where, basically.
Yeah? Okay, you want to qualify?
Do you want me to clarify?
So what goes where and
How it works together.
how it works together and what was given to you already?
Trying to figure out what was given to me already.
Right. Okay, and so, you have some program. It had, in our case, we had a nice observable structure. I think it's nice with a pattern. You had to figure out what the relationship was. You had to make that relationship distributed. Okay, so you had these internal producer-consumer relationships. You had to make them distributed. So there were these pieces that were linked together. You had to separate them, or you had to replicate them, so that when a command is executed here, entered by at one client, it's not only processed at that client, but it's also sent to the other end. Because you have to somehow trap the event, send it across, build some relationships. So that was the implementation problem, and you had to create these producer-consumer relationships. So basically, it was distributed separation of concerns. Okay, that we were looking at separation of concerns in 401, and now we have to do distributed. So that was the implementation challenge, right? And so that's what I'm saying, distributed separation of concerns. And here, you might already have a matrix multiplication code. You might have a lot of existing problems solved, done in 60s and 70s, and this is a real problem, okay? And how do you go and parallelize them, okay? How should you parallelize them from scratch is one issue, but how to take existing code and migrate it is a similar implementation issue. Again, a lot of work, a lot of research in this area has gone to try to accommodate existing code. And you can think of RMI being developed also to sort of accommodate existing code, that you just take a local procedure call, make it look like a remote procedure call. Similarly, you can imagine building constructs here that take an existing loop and somehow use the loop without any changes and make it parallel. Okay, that's sort of the ultimate. Okay? Questions? Okay, distributed systems and security tend to go together. Which case do you think raises more security problems? Yeah. First one, why?
Because when you're doing computation and you're splitting up something, the individual pieces of data don't really make sense.
Okay, so you're saying, the data don't carry anything useful.
Yeah.
If it's my DNA,
I mean,
my DNA doesn't matter. I'm happy to share it. Yeah, it's good.
I think computation distribution has a lot easier, like a significantly higher fault tolerance. It's really easy to verify if something's right or wrong. In the first case, I would also say that once you have a distributed network where you're sending multiple copies of something, I'm thinking databases for specific examples. Once you take chunks of your data and put it in multiple locations, you can have any of those locations compromised, and then that could affect the overall system. So if you're doing something that's more complicated than simple mathematical, like distributed programming, then you have a higher rate at which a compromise could occur, which would affect the whole network.
So you're saying in the second case, there is a higher rate of compromise. So compromise in terms of errors or compromise in terms of malice of some kind?
Well, I think security generally means malice. As far as errors go, that's just fault tolerance. And I think the second case is a higher degree of fault tolerance than the first, just because verification.
So fault tolerance and malice are different, right?
Yeah, so I think the second case is better handling with fault tolerance. And I
No,
also,
let's talk about malice. Let's talk about security.
for video games, for example, like when you have cheaters in games and whatnot, I think it's much harder to handle cheaters in a distributed network than it is in a non-distributed network.
Okay. So fault tolerance is another issue. And if you're, so let's talk about that a little bit before we go to security. So here, if something bad happens, you can just restart the computation, right? Whereas if my data in Dropbox got compromised, then that's a problem. Okay, so fault tolerance is yet another issue. But what you're saying is that here there can be, when you're playing a game, for instance, there are fewer trusted agents, right? So there's more autonomy typically there. Whereas here, you might be in the same data center, in the same location, so things are more under your control. It can be within a building if you want it to be. Actually, if you're going to distribute computation, you want the net communication cost to be small. So you might want to geographically localize it too. When you geographically localize it, security problems also diminish to some degree. Yeah, Nishit?
I would also say that in the computation distribution, it's easier to implement something like a BFT. Like you can just send.
What's the BFT?
Byzantine fault.
Oh, Byzantine. Yeah, because there is no.
So you can just.
These are all under your control.
Like 10 servers and just wait. But when you're doing something like a game and you only have like one client, like you either trust it or don't. So BFT becomes much harder because do you trust the client or not trust the client?
So Byzantine algorithms don't depend on the application, okay? The need for Byzantine algorithms, and we haven't talked about them in the class, so you're using some knowledge outside class. We talked a little bit about this, okay, way back in the start. So the need for Byzantine, traitor generals is less. And if the master created the slaves, it's probably, and these computers probably doing nothing else but doing that crunching, okay? So communication processes created independently on typically, autonomous hosts. So there's access control issues, there's trust issues, whereas you can probably have them all under control of one authority. But again, the line is blurred. So when I was in Madison, there was a guy called Miron Levy, a professor, who built a system called Condor, and the idea was to take all our computers and at that time that was the resource available, and use them to do some number crunching. And Madison was a systems place, so there wasn't really that many applications there that this was used for. But then later I became a professor at Purdue, and there was a professor called Sam Wagstaff who used Condor at Purdue, and he was always begging for computers because he was trying to discover prime numbers, which are now known as, I looked at Wikipedia yesterday, as Wagstaff primes. So you can have, and this is the meaning of the life example I was showing later, that we might want to get all our computers and use them to compute problems, look for life outside. So it's not as if that all crunching involves, computers under one authority. You could imagine people lending their computers. With all these smart computers with us, we can solve some very big problems if we just collect them together. Yeah.
I feel for the top four, there's more of a malicious activity issue than the bottom one because there's so many more points of entry for those.
No, but if I'm trying to find life outside, trying to find extraterrestrial life, I probably want anybody to give their computers to do that, right? So if I go, that doesn't happen typically. Okay, today, especially when with a little bit of money, you can get computers from Amazon or little or large, depending on your viewpoint. So, but imagine that we are pulling our computers together and allow any computer to join. You could be a malicious person that tries to fake life somewhere.
I mean, you're only looking for certain types of sets of data. While in these top four, you're so spread out.
So you're saying it's more restricted.
All your bases instead of like two.
Yeah. So you're saying, yeah.
Why is fault tolerance separate from malicious activity here? The whole point of the Byzantine fault tolerance
Yeah, that's Byzantine fault tolerance.
is that you have malicious information.
Right.
I don't understand why in any case malicious information is separate from fault tolerance.
Okay, so Byzantine, like I said, that's something we're not covering here, right? We're not looking at Byzantine. So you're right. I'm not disagreeing with you. I kind of said that.
So if maliciousness and fault tolerance are extremely related here, then they're equally vulnerable to a fault tolerance.
No, the chance for if what he's saying is right, and the computers are under my control, then there is no malice there.
So there's no reason to be malicious in number crunching. Like, what
Well, there's never any reason to be malicious.
All right, let's talk about like Wagstaff prime numbers. Wagstaff prime numbers are astronomically important to everyone who mines cryptocurrencies. So like, I would say that in the top category, or even in the computational distribution problem, you can make like a lot of money if you have a way to cheat the next generation of currency.
Okay, so can I just say this again, repeat again? When things are under my control, whether I'm solving prime numbers or something, yes, the chance of Byzantine behavior is less. Okay, when you guys are all in this class, I can trust you far more than when I'm teaching it to an online course. That's all I'm saying. Are you disputing that?
So what element of maliciousness are you trying to factor in if everything's under your control?
Oh, you deliberately, in your two-phase commit, you deliberately go and send the wrong value. That is Byzantine. That, when we're trying to do a proposal.
No, I understand Byzantine, but everything's under your control. Aren't you aware of what they're doing?
Right. So we haven't defined Byzantine here, but let me quickly define Byzantine as a program doing something that it shouldn't be doing. Okay? And when we are running our two-phase commit, we are all assuming that all clients and servers are behaving in a certain way. If they don't, somebody doesn't even send you back an accept response, you're stuck forever. That is Byzantine failure.
Perhaps we're down a rabbit hole.
Sorry?
I think we're down a rabbit hole, but I don't understand the distinction you were drawing between maliciousness and fault tolerant problem.
I'm not. I'm just saying the chance of Byzantine behavior is less when you can control the programs. Okay? Let's talk of fault tolerance versus security. So right in the beginning, we classified fault tolerance into non-Byzantine fault tolerance and Byzantine fault tolerance. And non-Byzantine, the fault tolerance is to tolerate system issues like message loss and computer failure, whereas Byzantine, we were looking at somebody maliciously trying to create problems, and that could be algorithm manipulation. So you're trying to do two-phase commit. Everybody's supposed to follow a certain algorithm, and some nodes decide not to, okay, just because they want to be uncooperative. So that's the Byzantine general problem. So again, blockchain is an example of an algorithm that's designed for Byzantine failures. Okay, so they're called failures, but it's really security getting into fault tolerance, interfering with fault tolerance. So if we so in this class, we're basically looking at non-Byzantine fault tolerance. And the point is that Byzantine and general security problems are proportional to the autonomy that different nodes have. Okay? So if all nodes, in your case, you don't have to worry about Byzantine failures because you are running all your programs on a particular computer. They're all under your control. Okay? Unless a virus got infected, unknown to you, they will behave as intended. And if they're all running on this particular building, again, there's probably some control over what the programs are doing. But the more autonomous the computers get, the less control you have, right? So, and we said that usually there's less autonomy in HPC because we're trying to make something high performance. We probably want the computers to be very close to each other. They're probably going to be in the same building, though we will have cases of high performance computing done using autonomous computers. So there's usually, and there is a non-usual case. So usually that's what happens. Okay, that doesn't mean that it has to happen all the time. Okay, what about the lifetime? In which case, you can talk about short lifetime and long lifetime. Which one would you say is short and which one is long? In general, meaning finding an extraterrestrial life will probably take a long time. Yeah.
The
which do I think is a longer lifetime?
Yeah.
And computation distribution.
It's longer?
Potentially, yeah.
I think it's the other way around.
Yeah, so the top ones need to be available always for anything to connect to. The bottom ones, you start and then you don't need until you're finished your computation. You're not, receive more data after you're done.
Okay. I was picturing all the operations at the top though, or like easier.
Oh, so the individual operations?
Yeah.
Yes, that's true. I'm talking the process.
Okay, then yeah, the top one, 'cause that just doesn't stop.
Yeah, and in your assignment one, I think we never terminate, we never even consider termination of the whole program, right? We just assume the programs will remain. If you did assignments, the extra credit assignment, you started it, right? Have you done the kill part?
Yeah, you have to throw an exception by waking it up.
So you basically have to go and terminate. When the computation is over, you have to go and make sure all processes die.
Yeah.
Okay? So there is a start point, there's an end point, and the whole idea when you do experiments especially is to see how long it takes to do that, especially when you run assignments. Whereas in our assignments, they were just long-lived. Okay? So long-lived process need to be explicitly terminated. Short-lived, it might, again, the computation might be forever. So there's always exceptions, but we're looking at the usual case. Okay, because we're going to build abstractions for the usual case and not for the unusual case. Okay. So while we're talking of that, there's this principle in abstraction design which says make the usual case easy and make the unusual case possible but not necessarily efficient or easy. Okay, so that's going to be our motto in general in systems and when we derive the abstractions. Okay, go back to that. Okay, so in one case you've got long-lived, in the other case you haven't got long-lived. I'm just repeating some stuff so it gets recorded again. And so in the case of non-HPC, there's coupling and things can get out of sync, and that can create problems. In the case of HPC, we're trying to divide work, so faults in one part will not affect the other parts. And more important, you can restart computations. You can restart the whole computation, or you can restart part of the computation and still merge it with the other computations. Okay, so did anybody attend yesterday's faculty recruiting talk here? You did, yeah. So there they were talking actually about fault tolerance and MapReduce, which is this high-performance algorithm. And, there's no extra layer added for fault tolerance there because you can just restart the whole MapReduce again. Okay. So that's fault tolerance. So this is again text that you can read when you study for exams. But very quickly, so you have independent long-lived processes at autonomous locations, and they're made dependent for resource sharing, collaboration, fault tolerance, lots of reasons. And in the other case, we have a short-lived process trying to do a computation fast. And we have consistency algorithms, and we have speed-up algorithms in the other case. We may use additional mediating server for our algorithms. And we might have a master process in the high performance case. Okay, and the division of labor between client and server, which something Gatti always likes to put things in the server. You guys have been talking about putting things in the client. So there's an issue there, what goes in the server, what goes in the client, and division of labor among master and slave threads is a big issue in this case. Yeah.
Sorry, I have a leftover question from security. We asked what has more security concerns, distributed or parallelized. What do we conclude on that?
If things are more under your control, as they are in high performance computing, especially because you're assuming the communication costs to be lower, then the security problems are lower. But if we are allowing computers to come from anywhere, then they're as much.